Okay, today we're still studying the oscilloscope, and what we're gonna do is we're gonna look at the FFT capabilities of the Tektronix TBS 1072C that we've been using for the last few weeks. Hopefully this'll work out. What I have here, let me take it out of that mode. How do you? Maybe I don't know how to take it out of that mode. Anyway, I've got the oscilloscope. Right. Oh, first let me lecture so we can know a little bit what we're talking about. The share screen. This is out of your textbook, and I can see you're seeing it there on the screen. This is a Fourier synthesis of a square wave represented by the sum of odd multiples of the first harmonic, which has frequency f. So if you wanted to get a square wave, it would produce the different harmonics, different odd harmonics at different intensities to produce that. I actually played, let me bring up Mathematica. And this is, if I grab, this is the manipulate. I'm going to move this slowly. You can see these, all these phasors going around, and you can see the black one. Let me see that. The black one is what's, that's the sum of all of these. The blue one, let me get it in a position there. The blue one is the fundamental. That green one is the third harmonic, the fifth harmonic, the seventh harmonic, and the ninth harmonic. And so for every one revolution of this blue, let's start over here. Every revolution of the blue, the green's going to go around twice. Oops, why is it doing that? The green's going to go around, I'm sorry, I said twice. It's going to go around 3 times. The blue's going to go around 5 times. The red's going to go around 7 times, and the purple's going to go around 9 times. And if you were to look at a time view of this motion of this phasor, it would make close to a square wave, and that's what we have. That's what we show in the text. Let's see, where is it? This one. We're seeing the same thing here. You see how as you add more and more waves, this is just the fundamental and the third. Here's the fundamental, the fifth, and the third, and then this one has up to 9 of them, I think. And you can see how it's turning into a square wave. And the more terms you add, the more it approaches a square wave. So the reason I'm bringing this up, this is chapter 17. It's not on electricity and magnetism, but we're doing a scope experiment, and this scope has the ability to, in case you're wondering, this is from chapter 17. You can look at it, and this is what we're going to be. This is what we're going to be seeing on the oscilloscope. We'll see if it's just a sine wave, we'll see this. If it's a square wave, we'll see a whole bunch of odd harmonics. This is a tuning fork, a flute, and a clarinet. We're going to try to play with sounds early later. But let me stop this share and let me get a good view of the okay. So if right now we just have a sine wave at 1,000 hertz, and you can see the sine waves up here, but down here is the FFT, and you can see that there's a single component right here. That's a single component. Now let's change this. Let's do waveform square wave. Now it's a square wave, and now you can see all of these. I wish I knew what. Let's see, cursor. I don't cursor. Let's do. There we are. Oops, wrong one. Okay, let's press and hold it. It says maybe I need to set this to 0. There's 0 hertz. Now let's get the second one, and let's move it. Press and hold to get course adjustment, and let's move it. And that's, you probably can't see it on there, but it's right there. F1, it says 875. There it says 1,000. So F1 is at 0. I've got the marker at 0. This one's at 1,000. Now, what do you think it's going to say on the next one that we find? Any guesses? This next peak, what should it be? 3 kilohertz. Remember, it's the odd for a square wave. It's the odd harmonics. And then you probably can't see it on the screen, but right there, F2 says 3 kilohertz. What do you think the next one will say? 5. I heard someone say 5. And there's 5 kilohertz. It says it right there. And if I keep going, this will be what? 7, 9, 11, 13. And you can see how it's all odd harmonics. There's no even, now there's a bunch of other little things here, but the main ones are these right here. Now let's just go back, and you'll see it disappear. Let's go back to sine. There's a sine wave up here, and we've just got that single one up here. Now, I don't know what a triangle wave. There's a triangle wave, and I see there's the 1, there's the 3, and there's the 5, but you can see it right here. It says F2 is 5 kilohertz. Let's I'm sorry. They're all odd, but there's only a few of them, and they fall off pretty quickly. They fall off pretty quickly. That one's 3. And of course, this one up here is 1. Okay. Now let's do an auto set. Okay, there's our signal. We have a 1,000 hertz signal. Now we're going to modulate it. I'm going to put this, take it off of standby, 1 volt, but we're going to oh, first I have to go over here and select modulated sine, and then I can just turn this where I can see it. This one's at 1,000, and this one, let's set this one down to about 100. (200 hertz modulation). You can see there's the little symbol there. It shows modulated sine. And let's do the auto set again. And there you can see we have the 1,000 hertz. We can adjust that. You can see that adjusts. So we want this at 1,000, and this is 100, 200, 300. Let's go back to 100. Now, actually, let's put this at 10,000. And so now we have a 10,000 hertz with 100 hertz, but I want to modulate it at maybe 1,000, because what I want to do is I want to look at the FFT, and what you should see is we should see 10,000, but we're also going to see we're at 1,000. We should see 10,000. We should see sidebands of 9,000 and 1,100. So let's see if we get that. So this is what the waveform looks like. Let me trigger that. This is what the waveform looks like. We've got a 10,000 hertz signal, and we've got a 1,000 hertz modulating signal. Now we do an FFT of it, and let's find what these are. Let's put the one cursor at 0. Let's see. Cursor. That one's at 0 hertz. F1's at 0 hertz. That was F2 actually. Okay, F1 is at 0 hertz. And you actually can't see it there. Let me raise the that didn't work. I wonder if I can expand the scale. FFT. They're actually there. The sidebands just happen to be larger than the if you look, if I move this one over, which one am I moving? Let's see, cursor. F2 now says 10 kilohertz. F2 down here says 10 kilohertz. And now if I modulate, let me not modulate it so much. Well, I can't see it. Anyway, it's modulating. I showed you without the modulation. Here, let's take this off. Without the modulation, there's 10,000. I don't know why we have those other harmonics when it should be there's 10,000. Let's turn on the modulation. That disappear. All those others disappear. But now, what do we have? We have cursor. If I, oops, cursor. Oh, I have to do all that over again. Which one's moving? Put that one at 0. And there's F2. Can you see? Let me get this a little closer. There's actually two little. Okay, let's go press and hold for the fine. And now we can move it. And right there, it's at 9.02 kilohertz. And if we go on the upside, that's 10.9K kilohertz. Those are the two sidebands. Let's make this a little bigger. Let's make it 2,000. Let's see, frequency. Let's see, can you see that on 13? They are moving out. 2,000. Let's move the cursor. Now what does it say? It says 11.8, about 12 kilohertz, and this other one should be about 8. 8.09. We can even go up. Let's make it 3. You can see the waveform up there, barely, but you can see it. But you can see these have moved out. It's 6.84, the sideband. This one right here in the middle is our not. It says 9.96. And there's that one says 13. So whenever you have a modulation signal, not only will you get the fundamental that you're modulating, in this case, 10,000, you're also going to get plus and minus the modulation frequency. So here we have 3,000, so we have 7,000 on one side. I wish there were a way to, can I expand? Not that one. I want the horizontal. Maybe that's a little better. Oh, I need to leave that one at 0. That one at 0. Let's move this one. This should be our fundamental. That says 7. What's this one say? That may be a second lower sideband. That's 3. That's probably just from the modulation. That's 7. This lower one is probably the 10,000. Let's push and hold to get it fast. Push and hold for fine. That's 10,000. So it's 10,000, 7,000, and 13,000. Let's move, push and hold for course. Move it over here. Let's go fine. And that's 13,000. Okay. Now, if I leave it on that scale and change this frequency, if I lower the frequency, will they get further away from the 10K, or will they move closer to the 10K if I decrease the modulation frequency? They should, if I decrease it, let me move it up. Remember that this one here is the fundamental, and these two are the sidebands. So let's decrease it. And you can see that they're moving towards the center to the 10K. And now you can see them moving away. Okay. All right. So that was that's what I wanted to show you all on the last thing I wanted to show you on this oscilloscope is that it's basically acting like when you do an FFT, it's acting like a spectrum analyzer. I actually have one on my phone. If you watch some of my videos, you've seen it. Let's see if take it out of the oscilloscope. Put this in very quickly because it may be too loud. Let me switch with this one. Okay, you could see now we're looking at this is 10,000. I don't know if you can, I don't know if you can see it. This one says 10,000. Let me move it. This one says 10,000. I can, that's if I turn it on again. Oops. I messed up. Well, that's okay. We can leave it at 1,000. Why isn't it playing though? There's the 10,000. I'm surprised we can't. Anybody hear the 10,000? I can't, but my hearing's kind of shot. There is a 10,000 hertz signal there. So basically on my phone, I've got a spectrum analyzer. It's not as nice. I mean, it doesn't have the cursors and stuff, but it does have, you'll see when I turn on the signal, you'll get the sidebands. So anyway, this one is called Spectrum in case you're interested on for your phone. And you can see it has, as I speak, it's here. I'm sorry. As I speak, it's hearing my voice and displaying it. And if I put it in spectrum, you can see that it's a broad spectrum. My voice is a broad spectrum. If we were to play music, you would see the different signals coming from the music. Okay. Any questions? I know this hasn't turned into an experiment, but it was the last demonstration of the oscilloscope. You know, we had done previous experiments with the just measuring the signals using the oscilloscope, getting the frequency and the frequency and the period and the amplitude using the cursors. We were able to look at an LR circuit. All of that's on the module that I released today. You can, so we measured the waveforms, we measured an LR circuit, we measured an RC circuit. I actually did that one after everybody had left because I wasn't having success with it when we were here in the class. And then we did a resonance circuit where we had a capacitor and an inductor, and we found the resonance. On the one I released on the video, it's 595. Last week, if you were here last week it was 600 hertz. I haven't presented that video yet, but just use the one that's on for your lab report. Use the one that's on on the video. Okay, and that's all I have prepared for today. You're welcome to stay. You're welcome to stay and work on your exam. You can work on it together if you want. If you have problems, you can ask me. But you might want to take the time to get started on that. Other than that, you're welcome to leave if you want to. Did everybody pick up a sheet for the last lab? Okay,